Hi everyone, I'm Wang Chen. Today I'm gonna present our paper, Learning Multi-granular Quantized Embeddings for Large-Vocab Categorical Features in Recommended System. This is a joint work with Derek, Ting, Xingyang, Dong, Li Chan, and Ed. We all from the Google Brain team. So this paper is about learning representations of discrete symbols, such as user ID, video ID, and so on. So to embed these ID features, we typically need to create a very large embedding table where each line corresponds to the embedding for a particular item. However, since the number of items or users can be very large, so the embedding table actually accounts for the most parameters in a recommendation model. So we find that the currently widely used Onehot embedding has several drawbacks. It has huge memory consumption, and it's unaware of inherent item similarities. Also, it's unaware of the long tail distribution, which is widely used in recommendation datasets. So our idea is to propose the multi-granular quantized embeddings, and it has three features. First, it's an embedding compression method, which can significantly reduce the embedding table size. Secondly, it's a clustering or quantization method, and this kind of clustering and quantization can be end-to-end learned. And third, our method is a multi-granular method, which means we adaptively assign the embedding capacities to items based on their frequencies. That is, we assign popular items with a higher flexibility, while we assign a lower flexibility to infrequent items. So our method is based on a recently proposed method, DPQ. So basically, we split the embedding into several subspace, and in each subspace we learn k centroids, and we quantize the subspace embedding into the nearest centroid. And during serving, we want to need the lookup or search process. We just need to store the ID. We don't just need to store the centroid. Then we can look up and recover the embedding. However, since as we mentioned, typically real-world recommendation datasets are very power law distributed. Like this is from MovieLens 20 million. So we hope we can adaptively assign different items with different flexibilities. So we choose this solution to endow our model with multi-granularity, which means we assign the head item can use all the centroids, while tail item can only use first k-tail centroids, while k-tail is typically less than the capital K. So by doing this, we can restrict the flexibility of tail items. And moreover, we can use a smaller storage for this kind of tail items, since we only need log k tail bits. So this is a diagram of how our method works. So for a batch of item index, we split them into head item and tail items, and we retrieve them separately. And finally, we recover the embeddings by assemble the two embeddings. We perform experiments on MovieLens datasets with several strong baselines, including low-rank factorization, scalar quantization, DPQ, and as well as the full embedding. So in here we can see our proposed method MGQE can achieve similar or even better performance with around like 20% of the model size. So for conclusion, so in this paper we propose MGQE, a highly compact embedding scheme. And we found the MGQE generally improve performance. This might due to the regularization effect. Thank you.